Chapter number 4, the processor. Today's lecture is about overview of pipelining. Why a single cycle implementation is not used today. Although the single cycle design will work correctly, it is too inefficient to be used in modern designs. Why this is so? Because the clock cycle must have the same length for every instruction in the single cycle design. So the longest possible path in the processor determines the clock cycle. This path is most likely a load instruction, which uses 5 functional units in series: the instruction memory, the register file, the ALU, and the data memory. And the last one is register file. Although the CPI is the overall performance of a single cycle implementation is likely to be poor since the clock cycle is too long. Historically, early computers with very simple instruction sets did use this implementation technique. However, if we try to implement the floating point units or an instruction set with more complex instructions, this single cycle design would not work well at all. Pipelining uses a data path very similar to the single cycle data path, but is much more efficient by having a much higher throughput. Pipelining improves efficiency by executing multiple instructions simultaneously. An overview of pipelining. Pipelining is an implementation technique in which multiple instructions are overlapped in execution, much like an assembly line. Pipelining is an implementation technique in which multiple instructions are overlapped in execution. Today, pipelining is nearly universal. Let's have an example of a laundry system. Uh, in a laundry system, the non-pipeline approach is that first place one dirty load of cloth in the washer. When the washer is finished, place the wet load in the dryer. When the dryer is finished, place the dirty load on a table and fold. When folding in finish, put the clothes away or in the cupboard. So these are the 4 steps normally performed during a laundry. When one lot is over, then start over with the next dirty lot. The pipelining approach uh, takes much less time, as in this laundry example. We see that as soon as the washer is finished with the first load and placed the load in the dryer, then the washer with the second dirty load is loaded. When the first load is dry, you place it on the table to start folding, moving the wet load to the dryer and put the next dirty load into the washer. Next, you put the first load away, you start folding the second load. The dryer has the third load, and you put the fourth load into the washer at this point at all. These steps are called stages in pipelining, are operating concurrently. As long as we have separate resources of each stage, we can pipeline the task, as you clearly see in the following picture. The reason pipelining is faster for many loads is that everything is working in parallel. So more loads are finished per hour. Pipelining improves throughput of a laundry system. Hence, pipelining would not decrease the time to complete one load of laundry, but when we have many loads of laundry to do, the improvement is in throughput, decrease the total time to complete the work. If all the stages take about the same amount of time and there is enough work to do, then the speed up due to pipelining is equal to the number of stages in the pipeline. In this case, there are four stages that are washer, drying, folding, and putting away. Therefore, pipelined laundry is potentially 4 times faster than non-pipelined. The same principle we see in the laundry example applies to processors where we pipeline instruction execution. For, for example, LEGV8 instruction classically takes 5 steps. First step, we fetch instruction from the memory. In step 2, we read registers and decode the instruction. In step 3, execute the operation or calculate an address. In step 4, we access an operand in data memory if necessary, and in step 5, if we have any data, then we want to write the result into the memory or into the register. So the LEGV8 pipeline we explore has these 5 stages. Let's have a comparison between single cycle and a pipelined implementation. To make this decision concrete, let's create a pipeline. In this example, uh, we see 7 instructions that are load register, store register, add, subtract, and or, and compare and branch to 0. In short, we in this example we see memory instructions, arithmetic instructions, and branch instructions. The average time between instructions of a single cycle implementation, in which all instructions takes 1 clock cycle, to a pipeline implementation. Let's assume that the operation time for the major functional units in this examples is as memory access for instructions take 200 picoseconds. Fetching data from the memory or from the registers takes 200 picoseconds, and ALU takes 200 picoseconds. Total time of operation. A register file read and write takes 100 picoseconds. So in the single cycle model, every instruction takes exactly 1 clock cycle. So the clock cycle must be stretched to accommodate the lowest instruction. So the table shows the time required for each of the 7 instructions. The single cycle design must allow for the slowest instructions. In this table, it is a load instruction, so the time required for every instruction is 800 picoseconds. Let's take three load instructions and compare their performance in pipeline and non-pipeline implementations. When we compare non-pipeline and pipeline execution of three load register instructions, the time between the first and fourth instruction in the non-pipeline design is 3 multiplied by 800 picoseconds or 2400 picoseconds in total. On the other hand, all the pipeline stages take a single clock cycle, so the clock cycle must be long enough to accommodate the slowest operation, just as the single cycle design must take the worst case clock cycle of 800 picoseconds, even though some instructions can be as fast as 500 picoseconds. The pipeline execution clock cycle must have the worst case clock cycle of 200 picoseconds, even though some stages take only 100 picoseconds. Pipelining still offers a four-fold performance improvement, so the time takes between the execution of these three load instructions is 3 multiplied by 200 picoseconds or total 600 picoseconds. Pipelining speed up. The pipelining speed up discussion into a formula. If the stages are perfectly balanced, then the time between instructions on the pipeline processor, let's assume ideal conditions, then the formula is as time between instructions in pipelining is equal to time takes between instructions in non-pipeline divided by number of pipeline stages. Under ideal conditions and with a large number of instructions, the speed up from pipelining is approximately equal to the number of pipe stages. So a 5-stage pipeline is nearly 5 times faster. So pipelining improves performance by increasing instruction throughput, in contrast to decreasing the execution time of an individual instruction. But instruction throughput is the important metric because real program executes billions of instructions. Designing instruction sets for pipelining. Number one, all LEG V8 instructions are the same length. This restriction makes it much easier to fetch instructions in the first pipeline stage and to decode them in the second stage. On the other hand, in Intel x86 instruction set architecture, when instructions vary from 1 byte to 15 bytes, pipelining is considerably more challenging. Modern implementation of the x86 architecture actually translates x86 instructions into simple instructions that look like LEGV8 instructions and then pipeline the simple operation rather than the native x86 instructions. The second point in designing instruction set for pipeline is that LEG has just a few instructions formats, with the first source register and destination register fields being located in the same place in each instruction. The third point is that memory operands only appear in load or store in LEG V8 instruction set architecture, This restriction means we can use the execute stage to calculate the memory addresses and then access memory in the following stage. On the other hand, if we could operate on the operands in memory as in the x86, then stages 3 and 4 would expand to an addresses stages, memory stages, and then execute stages.